Okay, so for today's deep dive, we are jumping into something pretty critical, a foundational challenge for some of the biggest language models being built today.
We're talking about the ones using that efficient mixture of experts architecture, the MOE models.
Exactly. And we're looking at a new solution from ByteDance Seed and Renmin University that seems to fix a really core disconnect in how they work.
That disconnect is what the researchers call decoupling. You see, in a MOE model, you have a central router that's supposed to send information or tokens to these little specialized experts.
Like a switchboard operator for data.
A perfect analogy. But the problem is, traditionally, the operator's decision isn't actually guaranteed to reflect what the expert is really good at.
So the router might think, okay, this looks like a math problem, and it sends it to the math expert.
hmm
But that math expert is actually, say, terrible at calculus, and the router just had no idea.
Precisely. They are decoupled, and this is where the new solution comes in. It's this extremely elegant auxiliary fix called the expert router coupling loss, or ERC loss.
And its whole job is to force that router and that expert to be on the same page during training.
It forces them to be accountable to each other.
I understand the goal, but,
Oh.
MOE is all about being sparse and fast. A constant check like this sounds like it could be a massive computational bottleneck.
And that is the truly groundbreaking part of this paper. The mechanism is just so efficient. First, they basically interpret the router's internal settings, its parameters, as the ideal description for the kind of tokens an expert should be handling.
Sort of like its perfect customer profile.
Exactly. Then they create these slight variations of that profile, which they call proxy tokens, and they use those to test the experts.
So they're manufacturing the perfect little pop quiz for each specialist.
That's it. And this ERC loss then enforces two very strict but very lightweight checks. First is what they call expert specialization. Each expert has to activate highest for its own quiz, its own proxy token, compared to any other.
Okay, makes sense. And the second one?
The second is precise routing. This ensures the expert responds more strongly to its designated quiz than to any other expert's quiz.
So it completely locks in that specialization.
It locks it in and makes sure the router's settings actually mean something.
Now let's talk about that efficiency, because this is where previous attempts, completely crashed and burned.
Oh, absolutely. Methods like autonomy of experts or AOE, it's cost scaled with the number of tokens in your batch.
Which could be millions, computationally ruinous.
A total non-starter for scaling. What's fascinating here is that the ERC loss operates only on n-squared activations, where n is just the number of experts.
And n is usually a small number, like 8 or 16.
Right, which means the computational cost is fixed. It doesn't care if you're processing 1 token or 10 million.
That is just massive. It means the overhead from this loss is basically nothing.
It's negligible. They reported it added only 0.2 to 0.8% during training.
And zero overhead during inference, which is when you, the user, are actually running the model.
And this efficiency led to just undeniable success at scale. We saw stable, substantial performance boosts on standard benchmarks like HelloSwag.
But the real test is always the huge models, isn't it?
That's the one. And the benefits held up when they scaled all the way to 15 billion parameter models on really tough benchmarks like MMLU. Those other methods like AOE literally failed to even train at that scale. The overhead was just too much.
So this is a genuinely lightweight fix that actually works in the wild.
Yeah.
But the paper also shows that the ERC loss gives us a powerful analytical tool, right, that could actually see the specialization.
They absolutely did. They used these TSNE projections to visualize the expert parameters. And you could literally see the experts go from being this messy, scattered cloud in a vanilla MOE to these tight, clearly separated clusters.
And they have a knob they can turn to, that hyperparameter, alpha.
Yes, alpha lets you explicitly control how specialized you want those experts to be.
And here's where it gets really interesting for anyone designing these models. They found that just cranking up that specialization to the max is actually a bad idea.
It's completely counterproductive, and that's the fundamental trade-off they uncovered. You need the coupling, you need specialization, but if you push it too far, the experts lose their ability to collaborate effectively.
And the model's overall performance starts to drop.
It does. There's a sweet spot.
So what does this all mean for you if you're the one building or optimizing these sparse models?
I mean, the ERC loss is one of those rare things in LLM research. It's a lightweight fix that delivers real, robust performance gains.
While also giving you these controllable tools to understand what's actually happening inside the model.
Exactly. And that brings us to the final provocative thought for you to chew on. The optimal degree of specialization isn't a fixed number. It's model dependent. They found an alpha of 1 was best for their smaller 3B models, but zero point 0.5 worked better for their 15B models.
So the challenge for the future isn't just about forcing this coupling to happen.
No. The real challenge is finding that perfect empirical balance point between expert specialization and system-wide collaboration for your specific architecture.
That's the new calibration problem we all have to solve.